Good morning, everyone. So this is my talk about Nintendo audio hardware and how we can emulate it with Elm. And this is what my emulator looks like. And you might have seen this before today. And here is running Pokemon. And I already talked about my project at Oslo MLA earlier this year, focusing on CPU emulation. And today I will talk about the audio emulation. This is a very complex topic, so I have only very little time, so we better get started. So how does the Game Boy work with sound? It's obviously not simply playback of audio files. That would not be very interesting, and I wouldn't be standing here today. But why not, and what did the Game Boy do instead? Remember, we are talking about a device designed over 30 years ago. Technology has evolved quite a bit since then. We have 8 kilobytes of RAM, a 1 megahertz CPU, and games had to fit on tiny ROM chips, often only kilobytes in size. And in this context, audio files require huge amounts of storage. Take the Tetris cartridge, for example. If we would fill the Tetris cartridge with the Tetris theme as audio, this is all we could store. That's 400 milliseconds. So compressing the audio data is also out of the question. We only have 1 megahertz to work with, and we actually want to have some gameplay, right? So the solution here is on-the-fly audio synthesis. Games send control information to a specialized chip that produces the sound based on given control parameters. This is similar to playing a keyboard. I select a voice on my keyboard and press a key, and out comes something like a flute that plays an A. And I only need to remember what key I pressed and what voice I selected to reproduce the sound later. I don't need to actually record it. This comes at the cost of a limited set of voices and limited polyphony. And this is also the reason why so many Game Boy games sound so similar to each other. Okay, that means we need to programmatically produce sound from scratch. And before we can do this, we have to know how sound works first. So I will give you a quick primer on sound, so you can follow along regardless of your prior experience with sound. It's probably nothing new for you that sound can be viewed as a wave, and the sound wave describes the change in air pressure over time. And our brain interprets this change as sound.
Hey, listen!
So this wave looked interesting, but we could hardly make any sense out of it, right? So we will dive in, and I will look at 3 characteristics of a sound wave and what they affect. First is waveform. This controls the timbre, sometimes also called tone color. And this is determined by the general shape of the wave, the waveform. This is a sine wave. And they sound very pure to us. And here's another wave that's squarey. It's a square wave, and it sounds like this. And it sounds different because of the difference in form, or waveform. The pitch you hear is determined by the frequency in which the waveform repeats. So as a baseline, here's the same sine sound again. And here we have the same sine wave, the same waveform, but repeated in twice the frequency. And it sounds 1 octave higher. And that's all frequency pitch is, just a change in frequency. And to drive the point home, here is what the wave looks like when we change the frequency during playback. Last but not least, there is volume, of course, and volume is affected by the amplitude of the wave. This is the distance between the 0 line and the highest point of the wave. And again, this doesn't change the way it sounds like, it just affects the volume. Okay, I think that's enough, so we can get started writing emulation code in Elm that produces waves. But when we write stuff in Elm, we usually want to start with a type, right? So we need a type to encode said waves. And I propose this type. It's a list of floats. But how would that work, right? So imagine the sine wave, and at the bottom you see the list that we want to represent our wave. And we will represent this by measuring the wave in fixed time intervals and put the amplitude of the wave in the list. And those measurements are called samples. And if we know the sample rate, the distance between 2 measurements, we can reconstruct an approximation of that wave from the samples. And this is what the approximated wave would look like. It's a bit more edged, but it still resembles our initial sine wave. And by increasing the sample rate, we could capture more nuance changes at the cost of size, because we need more floats, obviously, and time to measure the wave. In my emulator, I sample at 44,100 hertz, which means the distance between two measurements is 22.7 microseconds, requiring 44,100 floats per second that we need to create in our encode. Of course, I did not invent this encoding. This is almost 100 years old, and it's called pulse code modulation, or PCM. And today it's used everywhere where sound is involved. Like audio CDs are basically just disks full of PCM, and HDMI uses PCM to transport audio over the cable. But most importantly for our use case here is that the Web Audio API allows us to easily play back PCM data. Okay, we have the knowledge what sound is, how it works, and how we can encode it, so we can actually dive into the game more details and how we can emulate the audio processing unit, or APU. Quick heads up, this is only the tip of the iceberg. I had to streamline and simplify a lot of things that are specific to the Game Boy, so we're not sitting here for 3 hours and listening to edge cases in the Game Boy hardware. But nothing I tell you is blatantly wrong. Okay, this is a simplified view of the APU and what other components it's connected to. It contains 4 channels, channels 1, 2, 3, and 4. And each of the channels create their own distinct sound. They are different in terms of what the channels can do. More about this later. Then all the sounds that the channels produce are mixed by a mixer component into a stereo signal that the user then listens to. The CPU and the games obviously can change the state of the APU and the channels to alter, for example, the channel's pitch or the stereo mixing. They do so by writing to specialized RAM addresses that will be mapped into the state of the APU. And for our ELM case, that means that if in my CPU emulation code I write a value at a certain memory address, it will end up in an ELM record like this. This is the APU record, and you can see here that all the channels have their own state again. We have a mixing config that configures how we mix the samples together, and an audio buffer that will contain the samples, the floats that we will produce over time. And we don't play them like one by one. We buffer them for some time and then hand them off in batches. So channel implementations, this is where the fun begins, where we actually have to produce sound. All channels have 2 functions in common. So first is emulate, which will take an amount of CPU cycles and the current channel state. And it produces a new state, which is the same one as you passed in, but advanced by the amount of time you passed in. And a CPU cycle is roughly 0.24 microseconds in time. The other function is sample, which outputs the current sample based on the current channel state. And we will use this to produce our audio buffer. Channels 1 and 2 can only output pulse waves of different duty cycles and are therefore called pulse channels. And a duty cycle is the fraction of one period in which the signal is active. This is a fancy way of saying like 1 out of 8 steps the signal is high, as you can see here for duty cycle 0. And this is what they sound like. And this is the classic Game Boy sounds. Half of the channels can only produce these kinds of waves. I use a custom type to represent the available duty cycles in my code, and I also have a constant for each duty cycle, where I have an array that has the pre-calculated samples for that duty cycle. So I can grab them very quickly with array.get in a performant way. This is the core state of the pulse channel. You can see that we store the current duty cycle we are in and the position inside the duty cycle. Then we have a frequency that determines how fast we play back the wave. And as we've learned, playing back the wave faster results in a higher pitch. Volume is just a factor from 0 to 1, which we multiply our sample with to adjust the amplitude and therefore the volume. Of course, we need way more than those 4 values in a real emulator. For example, frequency is not enough. We need a counter that counts down over time so we know when we have to increase the position. But it's not very interesting, so I omitted it here. Sampling a channel works like this. We just grab the current sample from the current duty cycle at the current position and then multiply the sample we got with the channel's volume, and that's it. Channel 3 is interesting. Games can freely define what wave the channel plays back, hence its name. Games do so by copying samples that work just the same as our samples that we use internally to a special location in RAM. And this is the only channel that doesn't sound the same for each Game Boy game, and is helpful for things like Pokemon cries. Of course, we're talking about the Game Boy here, so there might be some limitations, and the limitations here are that every wave has to have 32 samples, and every sample amplitude is just 4 bits, so we have 16 different amplitudes we can encode. So that's not enough for like human voice or like real music. But we can use a triangle wave, or a square wave, or we can like go crazy and do something. Here's again the state for this wave channel, and you might notice that it looks very similar to the pulse channel, right? We just replaced the duty cycle thing with waveram, which is the array of 32 4-bit samples. And frequency, volume, and iterating through the wave work exactly the same as for the pulse channel. For sampling, we just need to convert the 4-bit value into a float by simple multiplication. Last channel is noise. It's channel 4, and it's quite different to the other 3. It just outputs random white noise. And games can control how coarse the sound is like by using one of 2 width modes. This is 15-bit mode, and this is 7-bit mode. And as you can imagine, this is primarily used for percussion and sound effects. As before, I encode the possible width modes in a custom type. And making possible states impossible is also important for emulation. The state here has 2 new additions that the other channels did not have. As this channel outputs a random value, we need to store what we last outputted, because it's totally possible that the channel is sampled at a higher frequency than the actual channel frequency is. So we might have to output the same random value again, and because it's random, we need to store it. The other value is a bit more cryptic. LFSR bits. And this means linear feedback shift register, or LFSR. And it's a simple piece of hardware inside the APU that produces a random string of zeros and ones. And the best part about it from our programmer perspective is that the output is totally deterministic. We can predict the output if we know the seed. And this means we can implement this faithfully to the original hardware in a purely functional way. It's so nice. How does it work? So we start with the bits that we have in our channel state. And to obtain the next random value, we just shift everything 1 to the right. And the value that's falling out, the one here, is the next random value we produce. And up to this point, this is just a simple shift register. But where do the other values come from? You might notice that a 0 appeared at the most significant bit here. This is where the feedback part comes in. So we take our 1 and the next value, the 0, store them together, and write the resulting value at the most significant bit here. So it feeds back into itself, and that's why it sounds the way it sounds. And for the 7-bit mode, we write it, this becomes the input, yeah. And for 7-bit mode, we write it to 7-bit instead. So this process of determining a random value happens very regularly, depending on the frequency. And the higher the frequency, the more often we output a new random value. And every time we generate a new one, we store it in current output. And this makes our implementation for sample very simple, because we can just take that value, multiply it by the volume, and are done. So we have covered all the channels, but there's one more thing. Some channels can modify certain parameters on their own over time if instructed to do so. And first is volume envelope, and all channels except the wave channels can do this. And in a nutshell, this is changing the volume over time. And if we let, for example, a pulse wave fade out, it sounds way more pleasant. And this is the standard way to mimic real-world instruments. Another neat trick is letting the volume raise and then fall again. So we have a wave at a beach, right? It's just noise. Implementation-wise, it's simple. We have a custom type for if we're going up or down, have the current volume, and the frequency in which we change the volume. And then we just need to check if we are already at the maximum volume if you go up, and if not, we increment by 1. And the same is true for the other direction. Channel 1 can also do a frequency sweep, changing the frequency over time. So there are 2 simple examples of what you can do with this. Or this. And this is meant for sound effects, like collecting a power-up or something. The frequency sweep implementation is quite complex, has many edge cases and weird rules that will go way beyond the scope of this talk today. So for that reason, I skipped the implementation. But the core is very similar to what we've seen before. It just changes over time. Cool. Now we have implementations for all the channels. We can advance their state by time and can sample them based on their state. So we're just missing the mixing. And for simplicity's sake, I will just skip stereo mixing and recreate a mono signal instead. And this is the function we can use to do so. So it takes a list of samples and produces one new sample in a way that if we play the sample back for our brains, it sounds like all the samples are playing back at the same time. And you might be surprised that this is just the average of all values inside this list. And that's actually what my emulator does. This is all we need to mix the samples together. And we use it like this. So every 22.7 microseconds, our sample rate, we sample all the channels and create one new mixed sample out of them. We then prepend the sample to the head of our audio buffer that we have seen in the beginning of this talk. And we are ready for playback. Speaking of playback, so the user actually needs to hear what we have produced, right? A list of floats is not very interesting. So by using PCM as a well-established standard, we can just use the Web Audio API, pass the samples to it, and play them back. Of course, we cannot interface with the Web Audio API in native Elm yet, so we have to use port. And this is the port I use. I just send a bunch of samples over and then fire and forget. In JavaScript land, I will just copy the PCM samples that we produced into a Web Audio channel buffer. And note that we do this in reverse because we created our audio buffer in reverse in Elm because it's faster to prepend to a list. Then next, we just create a buffer source and connect it to the destination of the audio context and start playback. And the user now hears what we have produced. And with this, we have all we need to produce the iconic beeps and blips of the Game Boy. In the end, we've just written one big function that takes an amount of time as a parameter and produces a list of floats. And that's really all it takes. So you can play around with this without building a Game Boy emulator, just producing some floats and play them back. If you can't get enough of sound waves, there's a talk later at 5:55 by Chad Stearns that has even more waves for your enjoyment. But before I go, I want to show you a demo I've prepared. You will see and hear the output of my emulator while it's emulating the Zelda intro. So everything you see in a moment is generated by Elm in real time. I've modified it to skip the mixing part and instead output every internal channel on its own so we can inspect them with an oscilloscope while it's running. So here we go. So you can see at channel 3 is the bass part, and you can easily you can see how the pitch is changing. And the thunder is the noise channel. Here's the effect I talked about, like we have noise channel and have a volume envelope that changes over time, and it sounds like the wave crashing on the beach. Also notice that channel 1 is mostly just a quieter and more delayed version of channel 2 that produces the echoey effect we hear, and this is something the game has implemented. And here we go. This is the intro emulated by Elm. And that's all I have. Thank you for your attention, folks.
Thank you so much for doing that. Okay, there will be no questions for that one. If you want to have, if you have questions, you can go directly to Malax. Manuel.